The following content is provided by MIT OpenCourseware under a Creative Commons license. Additional information about our license and MIT OpenCourseware in general is available at ocw.mit.edu.
Okay. All right, so let's continue then on this unit of kinetics. And today we are going to talk about temperature. And we're going to talk about collisions, and we're going to talk about activation energies and activated complexes. And we're still in chapter 13 in your book. So when we started this unit on kinetics, we listed a bunch of things that can affect the rate of a reaction. And let's just review what we've talked about and what we have left to talk about. So we talked about mechanisms of reactions, one step, two steps, fast steps, slow steps. That can affect the rate of the reaction. We talked about concentration of material. We talked about nature of material. Talked about first order and second order integrated rate laws. And so today we're going to talk about temperature. And then Monday we're going to talk about the use of catalysts. And then Wednesday, again, is a review. So we're right at the bottom of our list here of things affecting rates of reaction. So the effect of temperature. So if you're in the gas phase, there's sort of the qualitative observation that if you increase the temperature, the rate increases. So you've probably sort of thought about this, that if you want to make something go faster, you add some heat. So today we're going to talk about quantitative effects and how you can actually calculate a change in rate constant if the temperature of the reaction is changed. So here we go back to 1889, and that's when Arrhenius plotted rate constants versus temperature. And he was looking to get a straight line. So he found that if he used the natural log of the rate constants and he plotted that against inverse temperature, he got a straight line. And here is what one of those plots look like. So the rate constants are varying exponentially with inverse temperature. So on one axis we have the natural log of the rate constant, K, and on the other axis we have 1 over temperature. And so this is the equation that is being plotted. So again, we have the natural log of K on one axis, that's rate constant, and the other axis is 1 over temperature. And so if this is 1 over temperature on this axis, then the slope of the line is minus EA, activation energy, over R, which is the gas constant. So up here, activation energy, E sub A, and R, our friend, the gas constant. And the intercept of the line, then, is the natural log of A, capital A. And capital A has several different names. You'll see it listed in different books as different things. I think our book usually refers to it as factor A, or the pre-exponential factor, and it would have the same units as K. So if one plots rate constants, natural log of rate constants over 1 of temperature, one could determine the activation energy for a reaction or the factor A for a particular reaction. So these quantities, factor A and activation energy, are dependent on the reaction being studied. So there'll be a particular measured value for one particular reaction. So let's think a little bit more about what these quantities are. So factor A, is it temperature dependent? No, it's not temperature dependent. So what is it? Well, if we look over here, the natural log of A is going to equal the natural log of K at 0 over here. And that means when 1 over T is approximately 0. So at what kinds of temperatures would 1 over T be approximately 0? Really, really big. So factor A is the rate constant for that reaction at some infinitely huge temperature. So that's the maximum value you could get for that rate constant at really, really huge temperature. That's what it is. It's not temperature dependent. It's a quantity that's the sort of maximum rate constant at the biggest temperature you can think of. So that's what factor A is. What about activation energy? Is that going to be temperature dependent? No, it won't be temperature dependent either. You can calculate it. It's the slope of the line, so you can get it out of plotting these values, but it's going to depend on the reaction being studied, not the particular temperature. And this is going to be important in a few minutes because we're going to be talking about the effects of rate constants on different temperatures and looking at equations and doing some calculations. Okay. So we can rewrite this equation in a couple of different ways. So you will see that equation for the straight line that Arrhenius came up with. It's called the Arrhenius equation, and it can be written basically just reversing these two terms. I guess because it looks better that way. I'm not really sure why you can't just keep it like that. But you'll see it this way. And you'll also see it rewritten this way. So instead of natural log of k, you would see it as solved for k. So here the rate constant is equal to a, which is this factor a, this rate constant at infinitely huge temperatures, times e to the minus EA, the activation energy, over RT. So you'll also see this equation this way. So it's a way of figuring out if you know the activation energy and you know factor A, you can calculate rate constants at a particular temperature. So it's not only gases that behave in this way that exhibit this Arrhenius behavior, and you can apply these equations to other systems. And let's just look at one other example of something that behaves with Arrhenius behavior. What is this? Crickets. How many of you have heard crickets in the wild? Oh, almost everybody. Yeah, some people, I spent some years as a summer camp counselor. And we always had kids coming to the country from the city, and there would be crickets and bullfrogs, and these poor kids that grew up, you know, right outside a hospital where all night long there'd be ambulances going by and traffic and helicopters and all sorts of things. And they would sleep fine at home, but then they would come to the country and they couldn't sleep a wink because of all of this noise. The country is not as quiet as people think it is. Crickets will behave, they will respond to temperature, and so they actually chirp faster when it's hotter. So if you're out camping, you can count how many chirps there are in 14 seconds and add that to 40 and get the temperature in Fahrenheit. Has anyone actually tried this? Did it work? You think so? Did you have a control of a thermometer with you? No. Yeah, it probably works better if you don't actually have the control, but it should theoretically work if you can do a good job counting. So that's an example of a non-gas exhibiting this behavior. All right, so let's talk more about the activation energy. We're going to talk a lot about activation energy today. So activation energy, EA. So if you have two molecules coming together and colliding, sometimes they'll form products, and sometimes they'll just fall away back into reactants. So not every collision will result in product. Why is that? Only the collisions that have the right amount of energy can go on and form products. So really what activation energy is some critical amount of energy that's required to go on and result in a reaction. So only the molecules with that critical energy, when they come together, they'll go on to product. Other molecules will come together and they'll just fall apart because they won't be able to overcome this activation energy barrier. So let's look at the effect of temperature on the molecules that have critical amounts of energy. So if we plot then fraction of molecules versus kinetic energy. And we can look at molecules that have a low temperature, or molecules at low temperature. So there are some molecules at low temperature. And we can look at some fractions of molecules at higher temperature. And then consider the critical energy needed to react. So the activation energy. So molecules with that amount of energy or more will be able to react. And if you look at the fraction of molecules then that would have that energy, at higher temperatures, more molecules have that critical amount of energy. And at lower temperature, fewer molecules have that critical amount of energy. So temperature makes a difference. At higher temperature, more things will be able to react. And that's what gets into this observation that reactions occur faster at higher temperatures. More molecules have the critical energy needed to react when they're at higher temperature. At lower temperature, it's more difficult. Fewer fractions of those molecules have that critical energy, can overcome an activation energy barrier. So let's look at an example now of, if you know what the activation energy barrier is, figuring out different rate constants at different temperatures, how temperature is affecting the rate of the reaction. So the example that we'll look at is the hydrolysis of sucrose, and this is part of the digestive process, and digestion is a good thing. So let's look at this particular reaction. We're given an activation energy, so someone's measured the activation energy for the hydrolysis of sucrose, 108 kilojoules per mole. And someone's measured a rate, an observed rate, a K-obs, of 1.0 times 10 to the minus 3 per molar per second at body temperature. Now you're asked to figure out what would the observed rate constant be if you lowered that temperature, if you lowered it by 2 degrees to 35. So you could write two different expressions. You can use Arrhenius equation and write two different expressions. So over here we have the natural log of K1, the rate constant at one time, and T1 at that temperature. So the rate constant at temperature 1. And so that would be equal to the natural log of factor A. Again, that's not temperature dependent. Minus EA, the activation energy, and then it's over RT. And we write the same expression for a second temperature and a second rate constant. Now we can combine these two expressions and come up with one equation. So if we subtract, we have natural log of the rate constant 2 minus the natural log of rate constant 1. And that can also be expressed in terms of natural log of K2 over K1. And here we can pull out the temperature terms. So both of these have the same expression, minus EA over R, the rate constant, and now we have the two temperatures. So this expression is telling us how the rate constants are going to change with temperature for a particular activation energy. What does this equation look like? It should look familiar to you. Something that we talked about before. What was that equation called? Van Hoff equation. And instead of rate constants, we had what? Instead of rate constants, there were? Equilibrium constants. And instead of EA, we had what? What tells us about how equilibrium constants changes with temperature? If you have a reaction and you heat up the reaction, how do you know which direction it shifts? What's our predictive tool? Delta H, right. So this equation is similar to one we saw before. Here we're comparing how rate constants change with temperature, and a predictive tool is the size, the magnitude of the activation energy. Before we were talking about how rate constants change with temperature, and the predictive tool there was delta H. So in case you need a review of this, we will review this actually at the end of the class, because this is very exciting. At the end of the class, we come back to Le Chatelier's principle, and we can explain Le Chatelier's principle in terms of temperature in a different way than we did when we started the course, because now we can think about it in terms of activation energies and rate constants. So we'll see that Van Hoff equation again. All right, so for the moment now, we're just considering how rate constants are changing with temperature. So we can plug in our values. The initial observed rate for the reaction at 37 degrees, and we have K2 that we're going to solve for. We are given the activation energy, and we know the gas constant, and we're given the two temperatures. So the only thing, tricky thing here is to remember to get your units to cancel out. Often activation energies are given in kilojoules, whereas your gas constant is in joules. The temperatures here were given in Celsius, but if you're using the gas constant, you're going to need to convert them to Kelvin for your units to cancel. So the only thing tricky about this is to make sure that your units are going to cancel. And so we can solve this for K2, and K2 comes out to be 7.6 times 10 to the minus 4 per molar per second. So it would be the same units as K1, and that's quite a bit slower. So we only changed our temperature by 2 degrees, and yet the rate is quite a bit slower. So the body temperature are the reactions, the enzymes in our bodies, and how much they need to work, how well they need to work, is really optimized for the temperature of our particular body. So if your body temperature drops quite a bit, or if your body temperature goes up quite a bit, that's not good for the overall working of the human body. So just some advice for today, like a day like this. It's best to keep your body temperature at the normal body temperature. If you're spending a lot of time outside, wear a hat, wear a scarf, wear gloves, wear real shoes, not sort of flip-flop type things, and you should be able to continue to hydrolyze your sucrose and digest. But you have to start worrying about what clothes you're wearing this time of year in Boston, for those of you who are from warmer climates. All right. So if we look at this equation again, we'll see that if this term is large, if you have a large activation energy, if you have a large critical energy needed for that reaction to go, then that reaction will be very sensitive to changes in temperature. If this is a big number, then you're going to see a big difference between K1 and K2. So this will tell you a lot about the reaction, and we'll come back to this idea in a little bit. All right, so let's consider the reaction coordinate and activated complexes. So there's this critical collision energy, this activation energy that's needed for these molecules to actually react. So why does this happen? Well, as two molecules may come toward each other, they may not be able to react if they don't have that energy. Well, why do they need energy? Well, they may need to sort of rearrange. You know, a bond may be broken, an atom may fall to the ground, new reactions are occurring. There is energy needed to get your desired product. They have to distort. The bonds need to distort, and that requires energy. So the result is that usually before you go on to your product, say this is one of your products, that you need to usually form some kind of intermediate state, some kind of activated complex or transition state. And that transition state can either go on to products or fall back to reactants. And only those molecules with this energy can do this reaction, can overcome this barrier and go on to form products. And so I'll show you a little movie of two molecules coming together. They're going to circle each other and figure out if they have the critical energy to react. And when they have that critical energy, you'll know it, and go on to product. So let's just take a look at this reaction. So here comes molecule in red and in blue. They're checking each other out. Well, they had enough energy, and they went on and formed product. Okay. But only those molecules with that energy can go on and form the product. All right, so let's draw a reaction coordinate now and look at these activation energy barriers and these transition complexes. All right, so a reaction coordinate diagram has potential energy on one side and has the reaction coordinate on the other axis. And that just means the direction of the reaction. So a reaction will start with reactants with a particular energy. So in this case, we're going to look at NO2 plus CO. So we have two reactants at a particular energy. And then these will react. They will need to form some kind of activated complex up here. So say there's bonds distorting and new bonds forming. So there's some kind of intermediate state, some kind of activated complex or transition state. So there will be energy associated with getting up here. If they have the critical energy to react, they will go on then to products. And our products here are NO plus CO2. And these are our products. And so that's what the reaction coordinate will look like. If they didn't have enough energy, it would just come back down here. So this barrier up here is the activation energy for the forward reaction. And this over here is the activation energy for the reverse reaction. And overall, you have a delta E for the system. So the difference between the energy of the reactants and the products. So delta E is going to equal the activation energy for the forward reaction. The forward reaction minus the activation energy for the reverse reaction. And we can put some numbers on this. For the forward reaction, it was 132 kilojoules per mole. And for the reverse reaction, we have 358 kilojoules per mole. And our overall delta E value is going to be minus 226 kilojoules per mole. So minus 226 kilojoules per mole is going to be equal to the 132 kilojoules per mole minus the 358 kilojoules per mole. So these are all going to add up, and that's one of the equations on your equation sheet that you need to know for the final. That won't be provided. But it makes rational sense that these should all add up together. All right, so how does this relate? Delta E, what is this delta E? Well, this is a quantity that can be measured. It's a thermodynamic quantity. It can come from calorimetry experiments. And it's related to a friend of ours. It's related to delta H. So if you recall, delta H equals delta E plus the change in PV. And I think this was lecture 17 from Professor Sayre's notes when she started talking about thermodynamics. And so most of the time, these are pretty similar to each other. For gases, there's a little bit of a difference. This term exists. So you might have like a 1 to 2% difference, but it's more or less the same. So if it helps you to think about this as more or less the same as the delta H, that can be useful for you. They're very similar quantities there. Okay, so again, there's a barrier. And for this reaction, there's a smaller barrier going in the forward direction, the smaller activation energy, and a much bigger barrier for the reverse direction of this reaction. So if we think about activation energy barriers, every reaction is going to have some activation energy barrier. Just like most things we do in life have some activation energy barrier. For me, writing papers or writing grants, there's a very large activation energy barrier to get started. So the getting started part, and it's usually kind of more like this direction, this kind of size activation energy barrier. Once I manage to kind of get up over the hump, really get started, then it becomes much easier, and I can really get going with this. I imagine that if I recall back to studying for final exams, going back over the old material that you already covered and reviewing that, there is a sizable activation energy barrier to pulling out those first set of notes and pulling out exam 1 and looking at the things that you got wrong and going back over it has an activation energy barrier. And what we're going to talk about on Monday a little bit is some tricks to get over those activation energy barriers. Catalysts can lower the activation energy barrier. For most of us, an enormous level of stress can also help us get over that activation energy barrier. Your professor, for example, mentioning the final exam every day before class starts can be a little help getting over that activation energy barrier to start reviewing material. So this kind of plot you should feel like you should bond with this idea of activation energy barriers. You should understand at the deepest level about these barriers that these molecules need to overcome. All right, so let's look at the effect of temperature on whether molecules can make it over those activation energy barriers. So again, for an elementary reaction, there's always a barrier. There's always a barrier. Sometimes it's smaller, sometimes it's larger, but there's always a barrier to that. So there's always a positive EA here. Okay, so what happens if you increase temperature? So if you increase temperature, it should increase the rate because of this down here. You increase temperature, more molecules will have the energy required to make it over that barrier. So for an elementary reaction, increasing temperature will increase the rate. They'll get over the barrier. For an overall reactions, for a more complicated reaction that has multiple steps, it's not necessarily clear that temperature is going to have this effect. And let's consider why this is true. So let's look at the same reaction we looked at with mechanisms last time and figure out what all the K observed terms are. Are there small rate constants? Are there equilibrium constants? What does K obs really mean? And then we can think about how temperature would affect those values. So here we have a reaction with the fast reversible step, followed by another step that's slow. So we can say that the rate of product formation, our product here is NO2, is going to be equal to 2 because 2 are formed. K2, this rate constant, times this intermediate here, times the concentration of oxygen. So that's just this last step, this slow step, rate of formation of product. But this is an intermediate, so we're not done. We have to get rid of this intermediate. And here, we can do it fairly efficiently because we have a fast reversible step followed by a slow step. So we can approximate that this step is in equilibrium. And if we approximate that, then we can solve for this intermediate in terms of an equilibrium expression. So again, the first step, fast and reversible. The second step, slow. So this is pretty much in equilibrium. Not much of this intermediate is being siphoned off to products. So we can solve by setting up an equilibrium expression. So here's the equilibrium expression. Equilibrium constant for step 1 equals rate constant for the forward reaction over rate constant for the reverse reaction equals products over reactants. There are two reactants, 2 and O, so it's NO squared. And we can solve for the concentration of the intermediate then, which would be K1 times NO squared. So now we can substitute that in the overall expression, and we have this expression here. Now our K obs is going to be equal to this 2, K2, and big K1. So this is what we need to consider, how that's affected by temperature. Little k2 is an elementary rate constant. So for an elementary reaction, increasing temperature will always increase rate. So we know how this is affected. But now, and here's our expression that we looked at before. But now what about the equilibrium constant? An equilibrium constant, how do you know what's going to happen with an equilibrium constant if it'll get bigger or smaller with temperature? What's the equation that relates equilibrium constants and temperature? Van Hoff, right. So it depends on delta H. It depends on whether the reaction is endothermic or exothermic. And here's that expression. So you can see these are really very similar expressions. So here we have the equilibrium constants. Delta H is our predictive tool. Whether that's endothermic or exothermic will depend on what direction it goes. It'll depend on whether K1 is bigger than K2 or K2 is bigger than K1 with a change in temperature. And over here we have the expression that relates rate constants with temperature. And in terms of sign, that's not an issue here because activation energy is always positive. There is always a barrier to overcome. So that's always positive. There's never a negative barrier. So there's no sign change here, but there is an effect of magnitude of that value as there is with this. So it's not so simple. So if you have a multi-step reaction, it's not always so simple to predict what temperature the effect of temperature, because it may be changing one thing in one way and something else in another way. So let's consider this particular one here. Again, little k is always going to increase with temperature. The equilibrium constant in this case will decrease because it's an exothermic reaction. So this particular reaction is exothermic. So if we think about Le Chatelier, or we think about the Van Hoff equation, we say if it's an exothermic reaction, increasing the temperature will decrease the K, because you're going to shift the reaction in the endothermic direction to use up the heat. So the magnitude of the increase or decrease will depend on the magnitude of the energy barrier and the magnitude of delta H. So if we look at this particular example, and you're told for this particular example that the activation energy is a small number. It's not a very big activation energy barrier. And you're also told then that delta H is a big number, and it's a big negative number. So what would that mean then? Well, if you look at this, if you have a small number for activation energy, then there's not going to be a big difference between the Ks. So the rate constant's only going to increase a little bit, because this is a small number. On the other hand, if delta H is a big number, and you're told delta H is a big number, then you should have the equilibrium constant should be very sensitive to changes in temperature. You should see a big difference in the equilibrium constants, because this is a really big number. So this particular reaction is an example where increasing the temperature can actually decrease the observed rate. And the effect is because of the delta H. So again, a large activation energy means that the rate constant is very sensitive to changes in temperature. A large delta H means that the equilibrium constant is very sensitive to changes in temperature. So our predictors are activation energy and also delta H, and thinking about what might happen when the temperature of a reaction changes. And I mentioned this is always, that's always going to increase. Rate constant will always increase with temperature, and you can easily remember this, that there's always a barrier. You don't get a great deal. There's always a barrier to overcome. And delta H can be positive or negative, so equilibrium constants can increase or decrease with temperature. So for delta H, magnitude of delta H indicates the magnitude of the change. Sign of delta H indicates the direction of the change. And if you forget that, you could just look at the equations and they'll tell you the same thing. So now we can come back to Le Chatelier. So we can explain those observations about how equilibrium constants changed and how the reaction was affected, why you would shift in one direction versus another when you change the temperature. So again, Le Chatelier says that a system that's at equilibrium, if you have the system at equilibrium and you apply a stress, the system will respond in such a way to minimize that stress. So if you increased the temperature, the equilibrium should shift in the endothermic direction. That would be what the prediction would be from Le Chatelier, because if you put in more heat, the reaction wants to respond in a way to decrease the heat, and so it goes in the direction that absorbs heat, the endothermic direction. So this is what we talked about before, but now we can think about this in a little bit of a different way in terms of these reaction coordinate diagrams. So let's look at an endothermic versus exothermic reaction. So here we have an endothermic reaction. We have reactants here. We have a large activation energy in the forward direction, and we have products up here and a smaller activation energy in the reverse direction. For this exothermic reaction, we have a smaller activation energy in the forward direction and a much larger one in the reverse direction. So our equation here would then indicate you have an endothermic reaction. Your delta E is positive if you have a big number for the forward minus a small number for the reverse. So that's going to give you a positive overall number. Whereas in this case, you will have, if you have a small number here minus a much bigger number, you get a negative number for delta E, or an exothermic reaction. So if you're given information about the activation energy in the forward direction and the reverse direction and ask if a reaction is endothermic or exothermic, you can figure that out using this equation. So now let's think about temperature. So if there's a small barrier, only a small barrier, most of your molecules can probably get over that small barrier. Not that hard. But if there's a very large barrier, that's a problem. So temperature helps with the big barriers. The small barriers, the molecules are going over anyway. The bigger barriers, they need extra help. They need the help of increased temperature. So if we consider what happens increasing temperature here, the big barrier is the forward direction. So increasing the temperature will make it easier to overcome this very large barrier. Makes very little difference here. The molecules are already doing fine getting over the small barrier, but here there's a big help. So what this does then is it shifts the equilibrium toward products. So increasing temperature for an endothermic reaction shifts toward products. That's what we learned before, but we had a different rationale for it last time. Now let's consider this case. If you increase temperature, it's going to affect the reverse barrier more. That's the big barrier. This is where molecules are having a difficult time. This barrier, they're getting over that barrier already. So in this case, when you have this exothermic reaction, adding temperature is going to shift toward reactants. So it'll shift it in the endothermic direction, using up the heat. Again, this is what we saw before, but now we have a different explanation for why. So again, a large activation energy barrier means that the rate constants are very sensitive to temperature. It's highly affected. If it's big, it's large, it needs temperature for the molecules to get over. So increasing the temperature has a big effect. Now molecules can do it. They can get over. This is why a large barrier means that a reaction is sensitive to temperature. So big activation energy, big difference. Small activation energy, not such a big difference.